All right, so we're trying to come up with this new counting technique. So the name of our new counting technique is called combinations. And we use combinations when selecting a group of, let's say, R things from a collection of N things. So N is the size of the big group we're choosing from, and R is how many things I want in the group that I'm choosing. And the key thing when we're choosing this group is all that matters is what's in the group, right? Just like our subcommittee. All that matters is who did I pick to be on that team, not the order that I chose them in. Another way to think about this for other contexts is all of the things in the group, quote unquote, do the same thing. They're not distinguishable from one another in the sense that they don't have different roles or different responsibilities. It would have been different if in our subcommittee we picked a president and then a vice president and say a treasurer, because then picking a different person as president versus vice president, the order of that actually makes a difference. So we don't have that in a combination. It's just simply a collection or a group of either people or things. The fancy name for this, the number of ways to choose such a group, so choosing R things from N things, is called combinations of N things chosen R at a time. But the notation that we use is a big capital C, and then in parentheses we put the N and then comma R and close off the parentheses. So up here what we're going to do is learn a formula for that. A key thing to kind of keep in mind with the order of it, right, is N is the total. So the N, the number that comes first, is the total we're picking from. And then R is the number we are picking. Right, it's how many things are in the group. Now this formula that we're going to learn is going to take advantage of that factorial that we learned in the past last week. So that was why we practiced those factorials. We are going to have a division in this problem. What we're going to end up with is we're going to have in the top, we're going to have an n factorial. So notice that one is the large group, the total that we're choosing from. And in the bottom then, we're going to have R factorial, which R, remember, is the size that we're picking, the size of the group that we're picking. And then another thing, that's going to then be times the quantity n minus R, and then whatever that number is, factorial. So R factorial, and then times n minus R factorial. I want to go ahead and do the first problem from your worksheet together. So go ahead and grab that worksheet. What it asks us to do is it asks us to take the example that we just did, that with the activity, so from that office that had 5 people in it, choose a subcommittee of 3 people. And we want to use the formula to try and find that number. So we already know that the answer is 10 because we counted them using brute force. We just found all of the possibilities and counted the list that we found. But this time I want to use the formula. So when we use the formula, we have to think about 2 things. We have to think about, all right, the fact that we're choosing a group. So then in that context, what's the size that we're choosing from and what's the size that we're choosing? So here what we're doing is we're choosing or selecting a group of 3, that's the number we're picking, from 5, right? From the 5 people, we're going to pick 3 people, and we're picking a group of them. So that means that we're going to have a combination of the total is 5, and from that we're picking 3. So combination of 5 picking 3. So then let's try and put these in the place that they go in the formula. So on the top is n factorial, that's the bigger number. So 5 factorial is going to go up top. And then in the bottom, we're going to have r, the number we're picking, factorial. So that's 3 factorial. And then the quantity, n minus r, which will be 5 minus 3. And then once we find what that number is, we'll do its factorial. So let's just do that little piece really fast, right? What is 5 minus 3? Well, it's 2. So really this is 5 factorial divided by 3 factorial, 2 factorial. Which is what we found when this was the type of thing that we looked at last section without any context, right? We didn't know why we were evaluating these things with factorials in them, but it was for this reason, so that now we can just kind of do this simplification a little more comfortably. So if we remember what we did, well, we said, let's take the top and start to expand it out. So starting to write out 5 factorial, we've got 5 times 4 times, then what we decided to do was we said, let's always stop at the bigger of the 2 numbers on the bottom. So the bigger of the 2 numbers on the bottom is 3. So we've got 3, and then I'm just going to keep a factorial on 3, which indicates that really in this 3 factorial is the rest of 5 factorial. It's 3 times 2 times 1 is all inside of that 3 factorial. So then in the bottom, I still have 3 factorial, 2 factorial. And what we can do is we can say, well, this is 3 times 2 times 1, and this is 3 times 2 times 1. So we're going to cancel those 3 factorials out. Right, we'll cancel a 3, we'll cancel a 2, we'll cancel a 1. So then all I'm left with is 5 times 4. And then in the bottom, I have 2 factorial, which is 2 times 1. And then we can simplify the top and the bottom. So in the top, 5 times 4 is 20. And in the bottom, 2 times 1 is just 2. So then last, doing the division, 20 divided by 2 is going to be 10. Which is a good thing, because that's the answer that we had found before. So we're finding that answer in a different way, which is pretty cool and exciting. So if you need to recap that one more time, maybe go through it once more. But again, we found this idea that there are 10 unique groups of people. And this is a really good thing because as we can get the same picture up, right? Trying to answer questions the way we did the activity by brute force, by just actually listing them, is going to become very tedious the bigger the things are, right? Even with that one, it felt a little bit long, probably, and a little bit tedious when we only found 10 things. It wasn't a very long list that we were looking for. So this formula is going to come in super handy when we're dealing with larger groups of things. Now, one thing that I want to point out, we saw in the last video that there was this idea of if it was sequential counting, there would have been 60 things, and then each of those was counted 6 times. I just want to add a little note on the bottom. This is how I would choose to do it, is I would cancel the larger of the 2, but we could have instead canceled out the 2 factorial. So we could have done 5 times 4 times 3 times 2 factorial over 3 factorial, 2 factorial, and canceled the 2 factorials. It still would have worked just fine. And then what I would, been left with would be 5 times 4 times 3 divided by 3 times 2 times 1, which then that numerator is 60, and then the denominator is 6, which again gets us that 10. This is why the formula is set up the way it is. What it essentially does is it takes what we would have had with sequential counting, and then it divides out the duplicates. Divides out how many times we rewrote the one number extra times. So that's why there's some division in the problem. We can think about the fact that no matter what we put in this formula, it's always still a formula that's counting something, right? It's still always saying, how many ways can I count blah? So no matter what, this formula will always turn out to be a whole number in the end. The cancellation, the division is always going to work. It's always going to leave us a whole answer at the end. No decimals, no fractions left over. So it's a pretty cool formula. And what we're going to keep doing is just practicing lots of examples, trying to look for when does this apply, right? What does this look like in different contexts? And then we'll practice using the formula.